talk about a new set up here.
I mean, I don't want to actually.
Spend the entire day.
I was laughing so hard.
There's like people.
I didn't expect this whole.
I know, like bigger than Jesus.
Oh,
Yeah. I was like, I know that exists.
oh yeah.
You look a little bit higher up.
Why did they pick the CED for the projection on this? I don't really get it.
I guess I just get used to it.
They're great shots. It's a film. It's one of our series.
Yeah.
Pretty sure it's
Yeah, that should be it.
I mean, on the fly.
John, Chris.
Okay, yeah. Okay, yeah.
You're leading, right?
Oh, yeah.
Okay. Let's turn off the light.
You're a graduate. Oh, yeah.
Is that good light? I think we're fine, yeah. Okay, welcome to our weather discussion for this Friday. We have a special guest who will talk to us for a while after I give a little bit of a talk about some things we see on this weather map, and that's Chris Malcolm, who's a forecaster at Reno, Nevada, who's a former graduate of our program, both undergrad and graduate degree. And with some special insights on some of, I think, not only the weather, but some of the stuff that's been swirling around the weather.
I forgot my Sharpie.
Yeah, right. Everybody in NOAA has been provided with one now. Here's a beautiful picture of the hemisphere, a large part of the hemisphere this morning. Visible satellite image. Gorgeous cyclone that not only gave us some very dramatic weather yesterday evening, but also is now in charge of dropping the dew points through the floor, which is really nice. I think all of us agree with that. I mean, we had dew points in the low 70s for several days this week. And I will say this, that September humidity has a different feel to it than August or July. Maybe it's because I'm outside more in July and August. The temperature itself is often warmer. It just doesn't seem quite as oppressive as I feared it would feel. But nonetheless, it's nice to get back into the 50s for dew points. And look at that beautiful storm. It occupies really the central part of the North American continent, gigantic cloud head. And we had the trailing sort of squall slash cold frontal line come through last night with on its northeastern edge a really particularly potent amount of convection. Early in the afternoon yesterday, it was in Minnesota. It died down slightly as it crossed the river and then kind of revved up again when it came across us overnight and really gave us a really exciting night. Not only that, it's part of a large wave train. There's a decent, you'll see there's a decent upper trough that's just off, I guess, actually at the longitude of the Canadian Maritimes. One can get the impression from these low-level stratocumulus here that the wind direction is not only very obvious, but also extremely strong. And there's a strong upper trough feature that's developing up in this region. Very strong upper front, but it's going to sort of decay away to not very much. A little bit of development will go on south of the Maritimes, and then over about 2 days, it'll dissipate. Overall, a broadly zonal flow across the North Atlantic, and this is one on the far western edge of that zone, one departure of that. It's colder than normal in the southern part of the Labrador Sea, and that's evident it's colder than normal at 850. It's one of the only places in the Western Hemisphere where the 850 millibar cold air is outside its normal climatological bounds. And you can see quite a bit of what looks like stratocumulus in the Labrador Sea, especially south of Greenland. So that's kind of nice as well.
Hey, John.
That one can see, yeah.
So I'll just say one thing. It's probably the only time this semester I'll say it. That is a nice looking cyclone, but the only reason it captures anyone's interest, it's one of the first ones of the season. In a few weeks, it'll be a dime a dozen.
Right, and they'll all be spectacular and violent, and we get so used to them. We get weathered by them that we don't get that excited about them. Now compare the beauty of this presentation to this dilapidated whatever it is down here, and it's got an I in it at the Hurricane Center, something. It's called 9, actually.
95, yeah.
9. So this thing may actually turn into something substantial. It's looking considerably more convective along the sort of central Bahamas than it was yesterday. It looked even worse than it does now yesterday, but now maybe something's emerging out of this. Bad news for these poor people who are struggling to make it through the month of September after a terrible beginning to it, and they may be visited again, but hopefully something not quite as intense, but certainly they don't need anything on them at this point. And so this is the only feature in the entire North America, really. That's the cyclone. And it looks impressive. Central pressure is 1,004.2 right now. It's never been a very impressive storm. You can avert your eyes, but when these things are weak, they look terrible. Okay, so they demonstrate how weak they are. This thing looks vigorous, even though it's hiding only 1,000 millibar low, not even 1,000, 1,004. Still an impressive storm. Brought a lot of really dramatic weather to us. So we'll talk a little bit about elements of this, its downstream counterpart, and then also just a couple of elements about analysis that I'm trying to do about the whole nature of the cool season hemispheric flow. So I want to show you a couple of things that I'm working on, but struggling to get to work. It's kind of driving me crazy.
What are those waves off the East Coast? I see gravity waves perpendicular to each other.
Yeah, there's a whole series of them, right, moving down through the stratocumulus.
Yeah, and then there's the other ones too. See the streaks going the other way.
Yeah, 90 degrees.
At 90 degrees to those.
Yeah, I don't see them this time, but I've seen it many times before. Why are they polarized?
Well, it's
not
different shear
uncommon.
levels
It's
producing them, but
But 90 degrees difference is just, it seems to be almost characteristic, so maybe we can find something. If only there was some brightness to this.
yeah, we got harder to see.
Yeah, it's kind of hard to see, unfortunately.
We try this for this.
Yeah, it does.
Sorry, you don't get the color.
It's better than the Dark Shadows fan club that we just saw.
Well, it looks like the gravity waves are actually the ones that are east-west along the wave, and then those others
Is there something
are
underneath
more
maybe?
like coherent structures
It's
roll
very interesting.
structures.
It's really interesting.
in the boundary layer.
Yeah. Yeah, I don't know what that all is, but it's pretty interesting. And look at that, this is a nice picture. Again, you see all the river valley fog in New England early in the morning. Watch this, right along the Connecticut River Valley and others. Isn't that nice?
If you turn off the other light over there, you might get better contrast.
Oh, yeah.
It's the one closest to the door.
Of course.
Yeah, it's nice. And another element,
That's nice, yeah.
I think in this, when we look at the sea level pressure map, is this cold air damming occurring right along the east coast of along the Appalachians? That cloud mass that's kind of.
Oh,
parked
yeah,
up
I don't
against-
know, I don't know. There is a tendency for anticyclogenesis in this location,
Mhm.
definitely, because there's a northerly flow along.
And an
Very
easterly
strong
flow,
upper front.
yeah.
And so, yeah, maybe that's true. We'll see that in sea level pressures. And then when we get to some of the analyses with isobars on, we might see
Right.
it there as well.
There were some amazing gravity waves over southern Wisconsin and northern Illinois yesterday before that line came.
Oh, yeah.
I've got a loop of them, but I don't know if we have time for it, but I'll post it later.
Okay, let's go from here and take a look at the broad surface map. And we'll zoom in on our area. Look at this now, 57-degree dew point. I don't care about any of the other ops. 57 dew point is the thing that caught my eye. That's 15 degrees lower than it's been all week, but we're not far away from those high dew points. Over here in Indiana, with southwesterly flow, dew points are still in the 70s broadly, the whole state. It's nicer in St. Louis than it was yesterday, and the 70 dew points at that longitude much farther south. So trying to find the center of the circulation for this storm, it's somewhere up in southwestern Ontario, and I think that's probably the closest
Little
to the center of it. Huh?
A little to the northwest, maybe where it's almost calm. 042, just right.
Yeah, I'm trying to find the lowest pressure, and so I see 1,004 and 1,004.2, so it's about 1,004 millibars. Yeah, and that's probably the center of the storm right there. Light rain over in the western part of the storm, heavier rain to the north, and then widespread light rain, as you saw, with thunderstorms embedded. Here's one just over the border into Ontario in the northeast sector of the storm. So it's a pretty nice storm. It's too bad there's not time to analyze these maps and see what's going on. It's a little bit of a confounding map because there is a frontal boundary that's evident on the satellite picture, at least in the clouds, but it's not so clearly evident in all the wind fields and the pressure fields that, well, we can't see anything about the pressure field, but some of the wind fields, you've got light northerly winds all through Arkansas and Oklahoma. One imagines the front is certainly I don't know if it's gone that far to the south yet. I forget from the satellite picture. I don't think so. So there's some interesting stuff going on in the southern part of this where the winds, well, they're widespread, light northerly winds, temperature 96 over 65 in Birmingham, light northerly winds. It's not really impacted by the front associated with this storm. Maybe that testifies to the weakness of this event. It's only 1,004 millibars. It doesn't really have.
Well, you can see it very
Vigorous.
clearly. Look at Oklahoma, goes from 71 to 54 dew point.
Yeah, right in here.
Yeah,
But it still stays northerly all the way through there.
well, the
Northeast.
winds are on north, yeah, but I think there's definitely an air mass change.
Yeah, there's no question there's an air
Unless
mass.
it's dry line or
I
something.
wonder why it's not coincident with a pressure trough. It doesn't seem to be. That's what's interesting.
And then you can see the easterly flow over Delaware and Maryland and Virginia,
Yeah,
and the pressures are about 1,000.
1025, 1026.
And just to the north a little bit higher, so there is kind of a nose of higher
Yeah,
pressure
that's right. There
right in
is.
there. So when we look at
Yeah.
analysis, we might see some evidence of that.
It's 1031, 19 at New York City, whether that's Central Park or LaGuardia, I can't tell, but almost 1032, that's the highest pressure I see. Until you get to New England, it's even higher, 1033 at Chatham or at Provincetown. And strong winds, these are strong winds coming in here, 15 knots or so off the ocean. 45 dew point in Boston, so that's a 67 struggling to feel warm is what that is, with a 20-knot wind off the Atlantic Ocean. That's not a particularly nice thing. But it's probably a welcome change from what they've had, because I know it's been humid there as well.
Right, in the DC area, they had their, I think it was their 40th 90-plus day,
that
or
right?
97, the third warmest, or the third latest warmest temperature on record in National Airport.
Wow. Zach Handlos reports 3 days ago, we reported the 72nd day over 90 in Atlanta. They've had 3 since, so they've had 75 in there. 75 days over 90 in Atlanta, Georgia so far this warm season, and their normal is 42. So that's way out of whack. It's almost twice the allotment, and that's a large allotment to begin with. So that's miserable. Look at that, 95 again today. Just brutal. So a lot of interesting things going on around the country. This map requires a lot more analysis, unfortunately, but some of you also at the same time, we get to see some of the observations, which is always nice to do. Let's take a look at the radar summary right now. And it was equally attractive as the satellite picture last night, if you got to see this when this thing was coming through, or just hours after it had gone through. And so here's the remnants of the precipitation shield that is tied to the big cloud head that occupies most of Ontario province right now. And so to the northwest side over the Arrowhead of Minnesota, this light rain, temperatures in the mid to high 50s, and then some rain probably embedded with a little bit of maybe thunder and lightning, but not as much as last night. You see a few speckles of orange and red there going over Lake Huron, and that's now into southeastern Ontario. And that's the eastern side, the cold frontal portion of the storm. And there's a little bit of convection down over Oklahoma, parts of the Red River Valley, presumably tied with the same wind shift line and air mass change that's tied in with this cyclone. But it does lose its character further to the south. And then quite a bit of showers coming in off of the tropical easterlies over the panhandle of Florida, localized thunder showers. Do they drop little hail out of these things, or is that not characteristic down there? Just a little rain shaft, no hail? Yeah, no hail. Because when they look like this in the Puget Sound, they're all hail.
Sometimes very violent storms will drop a little.
Is that right?
But it has to be pretty big hail up high.
Yeah, it's so warm. Yeah,
I was going to suggest, you're speculating perhaps there might be lightning with some of those in Michigan and moving into New York State. We could take a quick look at the lightning data just
Oh,
to show
yeah,
students
sure.
we have that.
Yeah.
That data here as well.
oh yeah, there's a line of lightning. Few of the storms in Florida have over, but that's,
This is old, this is
How
from
old?
last night.
Yeah, so-
oh, it was last night.
There's, something's not, they're not getting data.
Oh, that's too bad. It's likely that some of the stuff that has the same character as today, that it has last night, maybe is lightning filled, but not as vigorously. That's too bad. Okay, I want to talk about that in addition to that. Oh, let's go to, I had another tab up, the Omega page. 12Z's not in yet because I've got to refix the times, but let's look at the 12-hour forecast made last night of the 700 millibar quasi-geostrophic from the GFS. And so here's our storm, and in consistent with its weakness in sea level pressure, it's not really got a very strong QG omega signal compared to the storm that's south of Greenland, which was kind of obscured by some of the higher clouds. That's a pretty nice couplet of ascent and descent. And then this one that's at the longitude of the Maritimes is predominantly descent. Two times as strong descent as ascent in this particular wave downstream. And so we saw cloudiness from this frontal region going back into this one that's over the Great Lakes in the satellite picture. And neither of these two storms is particularly that strong. The descent regions in both cases are stronger than the ascent region at 700 kilometers.
Can I mention something? These
Yeah.
omegas, right?
Yeah,
So just for the 141 class, omegas represent vertical motion. And so what you're saying is up and downward. That's
Yeah.
where the air is rising or sinking. Where the air is rising, generally you have cloudiness. So that blue area is where the air is rising. Right?
no, yellow is rising, blue
The
is
yellow
sinking.
is rising. So
Yeah.
that's where you would have cloudiness.
Right.
And the blue area is where you have sinking and then you clearing out.
Yeah, and we saw that really broad clearing south of Nova Scotia over Massachusetts Bay and the Gulf of Maine. That was on the satellite picture.
And those rising and sinking patterns are driven by the movement of these waves in the upper airflow. So as various features, you can see those thickness lines, those dotted lines there, those are wave-like patterns. As those progress from the west to the east, they cause these up and downward motions as they approach and as they leave. So that's what all this is about.
And we're going to go to the 500 millibar maps in just a minute because we can look at a movie to watch the approach of the wave that was responsible for our weather last night and the cyclone and its now frontal passage today. So that's kind of exactly what we'll do. But before we do, this is the total QG omega. Let's go to another tab there, Pete, and we'll look at the Sutcliffe Trendberth omega, which is just the vorticity advection by the thermal wind. And so it looks like a cartoony version of the last picture, but it doesn't really overturn the notion that you've got weak ascent centered in Ontario this morning, a stronger and a little more compact descent back behind it for the storm over us. Again, though it's enlarged in the area, it's a little cartoony. The ascent is weaker than the descent for the next wave downstream, and then they're about equal for the one over or south of Greenland. And this one looks almost the same as the total QG omega. The other ones are a little bit distorted. Now, if we separate the ascent and descent regions that are forced here by the rearrangement of vorticity in the vertical column, if we think about rearranging shear vorticity versus curvature vorticity, they sum to the total, you find something interesting. So let's take a look first at the shear vorticity advection, omega. Very little of this couplet associated with our storm has anything to do with shear vorticity being rearranged. Some portion of the descent over the Maritimes appears to have that relationship, and then some, substantial component of that couplet south of Greenland does. But this is a very different picture. Now let's look at the curvature vorticity advection. And again, the sum of what we saw for the shear ascent and curvature and shear descent would sum to the total. This looks like the curvature is driving this wave almost entirely. It's driving this wave predominantly. And it was about evenly split for this wave that's over us, which is kind of interesting. And every one of these waves and weather system associated with it will have a different characteristic along such lines. And so what I want to do is, I'm hoping this would set this up, we're going to at least be able to make some statement about the influence of the curvature on driving the ascent that gave us our sensible weather by looking at a historical look at 500 millibar maps from the prior week. So let's do that next. And that'll be just at our regular webpage, yeah. We'll do a Super Pete movie. And we'll stop right about there, maybe one or two back. Yeah, so this is now 7 a.m. on, was that Tuesday?
Wednesday.
Wednesday, okay. And here's the upper trough axis that's going to be associated with the weather that we had last night and we're having today on the backside, the cold side. And so, as Professor Tripoli was pointing out, if you look at these maps, the black lines are the geopotential height lines. They're equivalent of isobars at about 3 miles above the ground, 5.5 kilometers or so above the ground. And you can see, on any given day, you can see all kinds of waves in the atmosphere. And these waves in the mid-latitude atmosphere have associated with them characteristic distributions of all kinds of variables. One of those variables derived of another set called the ageostrophic wind is the ascent, up and down with vertical motion. So on a trough axis like this, by virtue of the fact that the flow at the base of the trough is slower than the geostrophic flow, and the flow in the downstream ridge and the upstream ridge is faster than the geostrophic flow, you end up with divergence of that non-geostrophic part of the flow concentrated, in this case, over Wyoming, and convergence aloft of it, in this case, over Northern California. So ascent region here, downstream of the upper trough axis, descent down here. So what I'm looking for, and a lot of us are looking for when we watch a map like this, or a series of maps, is how is this wave, how is this trough going to progress towards us? Will it change its shape? Will the curvature in the flow get enhanced? And all kinds of other things that might influence the divergence that leads to the vertical motions. So let's click ahead one more time, Pete. This will get us to, this is Tuesday night. The wave looks about the same as it did prior to that. It's getting closer. Let's keep going. Here it is on Wednesday morning.
Thursday
Thursday morning, with the day wrong. I'll just say the date. You can figure out what day of the week it was, because obviously I can't. So here's the trough axis. River started out over sort of central Utah to move closer to us. There's us. So we're still not in the perfect position to receive the bountiful upper divergence that's likely occurring downstream of that trough axis at that time. Let's keep going. This is Sunday night now. No, I'm just saying that to see if you're paying attention. Here's the trough axis. Here's us. It's encroaching on us. Okay, one more time. And that is this morning. And by that time, the upper divergence associated with that trough axis is over Lake Michigan, Lake Superior, and that's about where the central minimum in the sea level pressure was, 1,004 millibars. So this wave, as it approached, had an influence on dragging this cyclone across the plains into southern Canada and across us. So that's how we're thinking about the connection between showing you the vertical motion diagnostics and showing you the really abundant waviness that the atmosphere sometimes presents. Here over the Maritimes, where we had that really strong subsidence region in the forecast vertical motion field, that wave is very strong, tightly curved, and characterized by strong baroclinicity, unlike this one. This one's not so strongly baroclinic, and so that helps to enhance the amount of subsidence, in that case, on the upstream side of the wave that we saw evident in the satellite picture. So that's kind of interesting.
John,
Yeah.
people just commenting to me, the evidence on this, how very little baroclinicity there is at 500 millibars across
Yes.
much of the United States. Is that, I'm trying to think, it seems a little bit lower than you would I don't know, than I can recall this time of year.
Yes, I think you're right. Now, I'm going to say by proxy, I tried to bring my 850 movie of this year's -5 isotherm. For some reason, I don't think we have XANIM on this computer or something. That must be it, because I brought it over, but I couldn't run it. And it turns out when you see the movie, it's only 2 weeks old now. I only start September 1st. But we have, we had on the first couple of days of September some -5 air in central Canada. Got all the way to the border almost, and then it evaporated. And we haven't had anything that cold in the Western Hemisphere since. It's all in the Eastern Hemisphere. So the coldness, the baroclinicity is on the eastern side of the globe. There isn't much at 850 anywhere where you might expect there was a chance for it in mid-September in Canada. And in fact, we can look at the 850 millibar map right now and find the -5 isotherm. We're going to have to go pretty far north to get there. So there's a concentration of colder air in the Eastern Hemisphere that's really absent in the Western right now. And so I agree with you. I think that might be reflected also when you get all the way up to 500 millibars. This is impossible to see what the numbers are. That's -1 up in the archipelago. So this line here is the -5 isotherm. It is way up there. It's over Greenland all the time, and the central part of the Labrador Sea. Right here, it's a little bit colder than normal. Other than that, it's not colder than normal anywhere in the Western Hemisphere. And so that's a really far northern extent for this time of year for that -5 isotherm. 0 degrees is sometimes considered the line where autumn exists, and that only comes into New Brunswick. And everywhere else in the central part of the continent, it goes way up north of the north coast of Alaska. That's the 0 degree isotherm in 850. So this is not anything like autumn in this whole region of the North American continent. And despite that, we're able to spin up this beautiful looking cyclone with not much baroclinicity. So it's kind of nice. Wait till it gets colder. Just to our north, it'll be even more interesting. So these waves we're talking about are an interesting component of the flow in the mid-latitudes, and I especially get excited about them during the wintertime. So I've got a few panels here that I want to show you. I've been thinking about waviness of the jet stream and various ways to measure it. Other people are thinking about that too, and not really pushing the envelope very much. I think maybe we've got better insights on some of that than I've read other places. But I've got a couple of panels here I want to show you. I'm trying to convert this to not as good as looking at the potential vorticity at the tropopause. I like that much better for showing what I'm going to show you, but one can also think about the geostrophic flow on isobaric surfaces and make some statements about how wavy the flow is. So we click on this one, Pete. This is the 300 millibar geopotential heights every 90 meters from 6Z this morning. So this is from the GFS analyses at that time. So every 60 meters, I didn't label them just so you can tell, but you know, when the gradient is really strong, that's where the wind speed is going to be strong. And so one could, if one wanted, pay attention to every single one of these isoplex, calculate the wind speed, the geostrophic wind speed at every one of them, you know the orientation of the geostrophic wind, and then calculate the circulation around each of those isoplex. And then, once you know the circulation, you divide by the length of the contour and you get the average speed that corresponds to each one, the average geostrophic wind speed that corresponds to each of those isoplex. And then just pick the one that has the greatest average speed, and that will be the core of the jet, by definition, it seems to me. So when I do this on the GFS data, it works. It won't work on the NCEP data yet, I don't know why. But the next panel will show you that, at least this morning at 6Z, that value was 9,440 meters at 300 millibars, and that's in blue. So that's the core of the jet. And it even includes a couple of small cutoffs, because look at this, there's a wind speed maxima over Iberia and North Africa around this cutoff, and there's a little bit of one there over Central Europe. Okay, so that's kind of interesting. Once you know that line, you can figure out how wavy the flow is. Well, on certain days, this blue line will have a lot more wiggles in it than it does today. And then you can measure that from day to day and say something about it. Let me show you one last panel, just to give you an indication of how this is working, how I'm identifying that blue line analytically. These are the isotachs beginning at 30 meters per second. They're kind of ugly, unfortunately. I even smoothed them, but they're still ugly. Then that's 30, 40, 50. They go up every 10 meters per second. And here's my 9440 decameter meter height line. And you can see that that line cuts through the core of the jet in a lot of places around the hemisphere. It even collects a little bit of extra circulation because of its relationship to that wind speed maxima and the one here in Central Europe. Adjacent lines that I don't put on here because it starts to get ugly, sometimes they do better in the core of the jet at this longitude sector, but they do worse down here. So over the whole integration, this is the one that stands out as the core of the jet. I've done the same thing with the full wind along lines of constant PV, and I'll talk about that in October when I'm giving a seminar about the waviness that I'm trying to measure here. But I think you can do the same type of thing on an isobaric surface with the geostrophic wind. And incidentally, the picture of this line looks very much like the picture that you get if you use the PV isotels, but it's not exactly the same. In fact, this thing here is included all the way around. There's a whole big envelope that's included on the isotel picture, and so you get a little bit more wavy jet from that definition we do here. But anyway, I want to see, one thing I've noticed over the last 2 weeks, because I started doing this on September 1st, is it's remarkably consistent what value of the geopotential at 300 millibars consistently fits this definition of the maximum speed along its length. I didn't expect that. I thought it would bounce around quite a bit. And I'm waiting to see if I can get the other program for the NCEP data to work, if I can see this in a 70-year trend, if the middle of September always looks the same, or if it's been changing. So I'm hoping to see that. That's what I'm thinking about. So with that, yeah.
Just going to ask, the diagnostic that you computed is really an interesting one. I'm wondering, could an extension of this be used to identify circulation patterns in the winter, like the NAO? If you were to, or try to relate the circulation circulation that's about a contour that encloses, getting backwards. You identify a geopotential contour, calculate the circulation around it, and that gives you then the area average vorticity, let's say north of that contour.
Right, that's right.
Could you use that as some sort of index to define the NAO?
It would strike me that there's something lurking there, yes. There has to be, right?
Yeah, that would be an interesting diagnostic, because if it's a strong westerlies at some point, I don't think about these instances a lot. But
Yeah.
with the situation where you have the strong westerlies, you should have lots of vorticity north of that
Right.
contour, relative to Climo. And then when it's weakened or it goes into a different phase, it should have decreased.
And it's not only the vorticity will get weaker, but the area that's kind of the spine of the jet will be bigger if the flow is weaker.
Right.
And so you get a double whammy decrease in the circulation. I would think that is going to be a really nice way to pull something like that out of the
Where you've diluted the vorticity there because you have such a large
exactly,
area. Right,
exactly right. And so that was kind of related to something I have in the back of my mind. I'd like to know what the picture of this is as the winter goes on. And then you can pick out days where it's particularly wavy, pick out days where it's particularly not wavy, and then see whether or not there's any systematic structure to, or a systematic way in which a particularly wavy day looks in terms of the hemisphere. Are there places that have characteristic signals on those days versus days when it was open? And that would be really interesting. It's kind of, I'm sure there's something lurking.
Also,
anyway.
speaking of lurking, I
Yeah.
believe Melissa Breeden, Dr. Breeden's actually watching our broadcast.
Oh, is that right?
Yeah.
Oh, yeah.
She
That's
just
good.
sent a text about something a few moments ago about something we had just mentioned, and so she must be out there.
Oh, that's great. I'm glad to know that, because last week we were commenting on how it was so sad she wasn't here for the first time in like a decade or something close. So that's all I have. I hope to report more about this in the winter time. So go ahead, Rick.
I've been kind of watching this, but that low near Liberia,
Oh, this year.
yeah, that I think is a remnant of Dorian.
Oh, maybe. No. Dorian went straight to the
It
pole.
went straight to the pole.
Yeah.
It folded the tropopause over Scandinavia, and then it shot down and broke off into this piece over here over North
Oh,
Africa.
so there was a ridginess and then a subsequent upper front coming down the northwesterly flow or something?
Right.
Oh, okay.
So it actually came out of Scandinavia down to
Right there.
Iberia, and now this, in many ways, it's very similar to that Algerian storm I studied a
Yeah,
couple
that's
years
right.
ago with the hurricane that produces the anomaly in the Arctic, and then it just driven back down over Europe. So one of the things we can watch is see if there's anything substantial going to happen over the Mediterranean from this.
Yeah.
This is a very large PV anomaly now.
It's very intense wind speed max too. It's a 60 meter per second wind speed max.
Right,
Oh,
and it's a very
associated with that
deep
thing.
fold in the potential vorticity. So
That's interesting.
as it gets over the Mediterranean, it's worth watching
Yeah,
to see
sure
what
is.
that does.
And of course, the Atlas Mountains here play the same role in
Yeah.
this part of the world as the Mexican plateau does for us. And with the Gulf of Mexico being the equivalent of the Mediterranean, it's a really interesting area. Yeah.
So it could, if it's like that 2000 case, it could produce a superstorm in the Mediterranean.
Yeah, that's worth watching. Because this has been a persistent feature that's just been sitting there as a cutoff in this analysis for me the last 10 days. I've noticed it, but I didn't think about its origin. Okay. Chris, you're up next if you're still willing.
I am.
Great. Right.
So what were the dew points? What was it here?
56 maybe, 57? Yeah.
So I'm from Reno, Nevada, and if the humidity gets above 15%, it's like feeling really humid. So when I'm here for a trail race tomorrow, I'm probably right in the camera. And so I'm like, oh my God, I'm going to sweat up a storm. I'm not used to 57 dew point to me is like really humid. So I'm like, uh-oh. As John introduced, I'm the warning coordination meteorologist at the Weather Service office in Reno. And a lot of people associate Nevada with, that's where weather goes to die kind of thing. And in some respects, it can. The Sierra Nevada sort of play that role. But we get a lot of interesting and fascinating weather in Reno. In fact, just 2 of the last 3 winters have been some of the wettest on record in the last 130 years. That's some huge, huge winters. So it's been an exciting time to be there. And so what I wanted to touch on today is a feature that's going to come into the western U.S. on Sunday into Monday. It's probably our first legitimate autumn cold front coming into the west. And I'll show you a couple things for us in Nevada and California. That first autumn cold front, especially if there's not a lot of moisture with it, is usually a huge fire problem, a big fire weather issue. And so I was going to show a couple things, and Pete, I think I might just drive, if you don't mind.
Yeah, no,
I'll
that's fine.
come over and drive and show a few things. So, the Weather Service, we have AWIPS, which is our official system, but to keep it real, most of our forecasters, including myself, go to Tropical Tidbits or Pivotal Weather or something like that to look at actual data. So looking here, this is a 12Z GFS, and I'm just going to go just a quick 500 millibar normalized height anomaly here. I'm kind of stepping through time. So there's 0Z Sunday and 12Z Sunday. Well, this feature here definitely catches your eye. 500 heights dropping down to about -2 standard deviations below normal, maybe a little bit more. And so that's 0Z Monday into 12Z Monday, and then going on to 0Z Tuesday. So some pretty significant negative height anomalies there across a good chunk of the western U.S. And in this kind of case, and I'll show you some details, it tends not to be a lot of moisture, but we get a heck of a lot of wind out of these kind of systems. And so forecast highs at Reno, for example, on Sunday are going to be near 90. Our average high this time of year is about 80. And on Monday, the forecast highs are near 60. So when you see a 30-degree drop in temperature from day to day, you're going to get some wind out of that. And that kind of goes along with these height anomalies here. So to kind of go back, looking at the forecast for the pressure gradient and the precipitation here. So as we get on into late in the day on Sunday,